Hi, my name is Matteo Masoni. I'm a researcher for the Università di Pisa, and today I'm going to talk about our researches in disturbance-aware minimum uptime planning strategies for motorsport vehicles in collaboration with the Politecnico di Milano on the project STAVE. Minimum uptime optimization is widely used both in motorsport engineering and in autonomous racing. Offline, it is used to generate reference trajectories and control inputs that help in tuning the vehicle setup and defining race strategies. Online, the resulting trajectories are often used as feed-forward references for advanced driver assistance systems or for autonomous driving controllers that aim to follow an ideal lap as closely as possible. However, standard minimum uptime planners are almost always formulated with deterministic models and not explicit representation of disturbances. As a result, the optimal trajectories tend to exploit the full envelope of the vehicle in terms of tie grip and track limits. This means that the planned path often runs extremely close to physical and safety constraints, so that even relatively small disturbances or modeling mismatches can push the real vehicle outside the feasible and safe region. The dynamic model we use for this study is a single-track model with nonlinear tire characteristic of Pacheco type. To represent uncertainty, we treat the disturbances acting on the vehicle as additive Gaussian process noise with zero mean and unknown covariance metrics that may depend on time. Under a first-order approximation, this allows us to describe the random state of the vehicle as a Gaussian distribution with a mean vector and a covariance matrix. The mean state follows the deterministic dynamics defined by the vehicle model, while the covariance matrix evolves according to a matrix differential equation driven by the Jacobian of the dynamics and by the disturbance covariance. In our framework, safety constraints such as remaining inside the track boundaries or staying below the tire friction limits are not enforced deterministically, but instead they are required to hold with a given probability. By linearizing each constraint around the mean state and exploiting the Gaussian distribution, we can transform the chance constraint into a deterministic inequality that involves only the mean and the covariance. The result has the form of a nominal constraint evaluated at the mean state plus an additional backoff term that depends on the covariance. The two key constraints are friction limits monitored via axial saturation ratio S at the friction ellipse and track limits monitored via lateral deviation E from center line. Both use covariance-based backoffs that shrink the feasible region. The figures show the original constraint bounds with the gray shaded area representing the available region when the backoff is applied. This backoff is given by a coefficient gamma multiplied by the standard deviation of the linearized constraint, where gamma is the quantile associated with the desired confidence level P of a standard normal distribution. In practice, gamma becomes a tuning knob for the safety level. For example, gamma equals to 3 corresponds to about 99% probability. Larger gamma or larger covariance produce larger backoffs, which in turn yield safer but more conservative trajectories. The first planning strategy we propose is an open-loop, horizon-based covariance propagation method. We work on a spatial grid along the track, and at each grid point we propagate the covariance forward for a finite number of steps h without considering feedback. Specifically, at a given grid point k, we have a fresh covariance pk0 in red that is newly initialized with a nominal initial covariance and a most propagated covariance pkh that has been advanced over h steps starting from an earlier point. When enforcing the robust constraints at grid point k, we use this most propagated covariance pkh in green to compute the backoff terms. This corresponds to a conservative worst-case view in which the disturbances are allowed to grow freely for each steps before any corrective action takes place. The design parameter h can be interpreted as the time window over which the driver or controller is essentially open loop before reacting to disturbances. The second planning strategy is a closed-loop covariance-aware method that explicitly incorporates a feedback policy designed to mimic the behavior of an expert driver. This approach is structured in 3 steps. In the first step, we compute a nominal deterministic minimum time trajectory using the standard, not robust, optimal control problem. The output is a reference path and control profile that ignore disturbances but serve as a baseline. In the second step, we design a discrete time linear quadratic regulator around this nominal trajectory. This feedback law approximates how an experienced driver or an advanced controller will react in order to track the nominal trajectory. In the third step, we reintroduce the stochastic framework and formulate a new robust planning problem in which we jointly optimize the mean trajectory and the feedback gains. In this problem, we propagate the covariance under the closed-loop dynamics, that is, using the linearized system matrix A minus BK, and we enforce probabilistic constraints using the resulting closed-loop covariance. We denote TLC a trajectory with robust track limit constraints and FLC a trajectory with robust friction limit constraints. The TLC trajectory, shown against nominal norm, tends to deviate more from the nominal line, and in some sectors it even enables slightly higher speeds, because it reshapes curvature while maintaining margin to the edges. The FLC trajectory, instead, stays much closer to nominal in terms of path geometry, but usually adopts slightly lower speeds, reflecting its more conservative use of friction. To empirically validate the benefits of the robust planning approach, we simulate the controlled vehicle under random disturbances. We perform 100 simulations with random initial conditions and Gaussian noise realizations, using the same covariance matrices for the initial state and for the process noise as those employed in the planning phase. We then compare 2 scenarios. In the first one, an LQR controller tracks the nominal, non-robust minimum time trajectory. In the second one, a controller tracks a robust trajectory obtained with the closed-loop planning method. When tracking the nominal trajectory, many of the simulated paths violate the track limit constraints, particularly in the more demanding pairs of the sector. In contrast, when tracking the closed-loop robust trajectory, almost all simulated paths remain within the tightened track boundaries. This demonstrates that the probabilistic backoffs computed during planning translate into significantly fewer constraint violations in closed-loop operation, confirming the effectiveness of the proposed approach under realistic disturbances. We test 2 professional drivers. One, labeled VP, has Formula SAE and sim racing experience. The other, MM, has a rally background and is overall more experienced in high-performance driving. The simulator rendered a high-performance car on the Cartodromo di Siena circuit, scaled by a factor of 2 to match the vehicle dimensions. We used a 1 meter wide racing ribbon overlaid on the virtual roadway. The ribbon center line corresponds to the planned trajectory. We tested 4 scenarios, 3 reference-guided conditions, NOM, TLC, and FLC, plus the non-ref baseline with free driving. For the disturbance-aware planning, we use a finite horizon of h equal to 4 steps to propagate state uncertainty, and a safety factor gamma equal 3, corresponding to approximately 99% constraint satisfaction confidence. To evaluate the results, we focused on a set of performance and style metrics. The primary performance metric is lap time in seconds computed over valid laps. To quantify steering workload, we introduce what we call steer energy, the integral over time of the squared steering wheel rate. Intuitively, higher values of this metric correspond to more intense steering activity and therefore higher physical effort. We also use several root mean square quantities. For tracking fidelity, we consider the root mean square of lateral position error with respect to the active reference and the root mean square of the speed error. These capture how faithfully the drivers follow the plan line and the speed profile. For style indicators, we look at the RMS of driver's side slip and compare it with the RMS of the side slip implied by the reference trajectory. And we also monitor the RMS of steering wheel rate as a quality proxy for steering energy. In the figure showing lap time distributions, you can see box plots for each combination of driver and trajectory type. For driver VP, NOM is clearly the fastest condition. For driver however, the medians for FLC and NOM are almost superposed, with overlapping interquartile ranges. This means that for FLC essentially preserves lap time while changing the way effort is distributed. TLC, as expected, is lower for both drivers. Its medians are several seconds above NOM and the boxes sit visibly higher in the plot. This is consistent with the idea that maintaining explicit margins to the track limits leads to somewhat longer paths and a more conservative use of speed, which costs time. The non-ref condition also tends to be slower and more variable, especially for where the whiskers are tall and the median lie above both nominal and FLC. Turning to steering effort, the steer energy figure is plotted on a logarithmic vertical axis to make differences more visible. Here, NOM and NOREF for occupy the top of the plot, indicating the highest steering workload. In other words, driving either under a purely time-optimal reference or with no reference at all forces the drivers to work hardest at the steering wheel. In contrast, both FLC and TLC achieve a marked reduction in steering effort for both drivers. For VP, FLC yields the lowest median steer energy among the reference following conditions, while TLC is also much lower than NOM. For the ordering is roughly TLC, then FLC, then NOM, with substantial drops in median steer energy when moving from NOM to the robust references. The key point is that robustness-oriented planning, especially FLC, can reduce steering effort dramatically. The lap time versus steer energy scatter plots make the trade-offs even clearer. In the overall scatter, points associated with NOM cluster along the lower edge of lap time, but sit high in steer energy. TLC points sit further to the right, with longer lap times but also lower in steer energy. FLC points form an elongated band that lies near an empirical Pareto front. They offer reduced steering effort for lap times that are close to those of NOM. First, we observe a clear drivability trade-off. FLC positions itself on what we might call a reduced effort comparable time band. For driver the lap time gap to NOM falls within the interquartile range of the NOM distribution, meaning it is statistically indistinguishable from the nominal benchmark. For driver VP, there is a penalty of about 1 to 2 seconds, but this comes with the lowest steering energy among all reference following conditions. Although our sample size are modest and these results should be considered preliminary, the trend is consistent and encouraging. FLC appears to offer a favorable compromise. Second, we find that robustness tuning acts as a conservatism lever. TLC achieves the lowest steering energy in several configurations, but at the cost of a marked increase in lap time. Its margin-keeping geometry discouraged the decisive corner cutting that racing drivers naturally prefer, lengthening paths and depressing apex speeds. Subjectively, drivers reported that TLC trajectories feel less natural to execute, even though they require less corrective steering. This suggests that while TLC is effective at reducing workload, it might be too conservative for contexts where the lap time is the primary objective. Third, we observed strong driver modulation effects. The lap time penalty under FLC is driver dependent. the more experienced driver, preserves pace and in some cases even exceeds the planner's reference lap time by operating with lower margins than those assumed during calibration. VP, on the other hand, trades time for effort, accepting a slightly slower pace in exchange for reduced steering workload. This indicates that skilled drivers can exploit residual margins in their robust references, whereas less experienced drivers benefit more from the stabilizing guidance. Moreover, free driving under NORF is systematically dominated for board drivers. It is slower and more effortful than reference guide driving, reinforcing the value of the structured trajectory planning. Putting all of these together, disturbance-aware robustness-embedding planning produces three distinct operating regimes. NOM remains the lap time benchmark but imposes the highest steering workload. TLC achieves the lowest steering effort but at the cost of noticeably slower laps, which is usually unacceptable in motorsport-oriented applications. FLC occupies the middle ground, lying close to the empirical lap time versus steer energy Pareto band. It delivers substantial effort saving with only marginal penalties in lap time, and in one driver's case, essentially no penalty at all. Future work should address three main directions. First, more drivers, more tracks, and longer exposure. A larger participant pool will clarify how skill and style modulate these trade-offs. Different track layouts will test whether the patterns hold across driving regimes. Longer sessions will reveal learning effects and adaptation. Second, richer workload indicators. Beyond steering energy, we should include cognitive and psychological measures, heart rate variability, eye tracking, or even pupil dilatation. Third, tighter coupling between planner and driver models. Currently, the planner ignores driver behavior. Integrating driver models could produce references tailored to individual characteristics, adjusting complexity to skill level and co-optimizing trajectory and guidance interface. Our long-term goal is to make robust, disturbance-aware planning a standard tool for simulator-based training and controller validation. Thank you.